Now we want to start looking at some of the infrared LEDs and detectors that are available in the shop for application for this project. There's more here than you would need, so you can make a choice on which one you want. The trade-offs are, the variables are always these things over here. That is the beam width, essentially the beam width of the device, and the radiant intensity. So the radiant intensity, essentially the brightness of the device, and the beam width, that is how wide that radiation is. So and you know, you may want to use something that has a narrower beam width or a wider beam width, and that's your choice. And then the third thing, of course, the other decision is the frequency of transmission. That is the optical frequency. And there's two of those available, and one in the 800 nanometer region and one in the 900 nanometer region. So if we look at this first one here, this is the SFH484, and we can see that that's a fairly, it's a device that has a fairly narrow beam width, plus or minus 8 degrees, and 50 milliwatts per steradian at a particular at a particular drive current. Now, in some of these devices, you can change that drive current, increase that drive current, and get a larger intensity out of it. So you need to check the data sheets to see if that's possible for the device that you choose. So the companion, or I should say another device that's a kind of a companion to 484 is the SFH485. That's on the next page. Now we have some of these. These are devices that have gone obsolete. So in other words, we can't order any more of them. I think Tom said that we have 10 of these, and they are the fairly narrow beam device. But the one that we'll talk about on the next page, the SFH485, we have about 90 of those, and in fact, along the way, I may be looking to replace these with an equivalent device, but go ahead and use these until we use them up. So that's what we have for the first infrared LED. So let's take a look at and compare this one with the SFH485. So here's the SFH485. And you can see right away that the specs are a little different on this one. In fact, the diagram looks different. It looks like the main lobe, intensity lobe, is wider, and sure enough it is, plus or minus 20 degrees instead of plus or minus 8. And the wider radiation pattern results in a smaller distribution of power over the angular component radiation pattern of the LED. So it's a choice. This one's a little wider than the other one. You may not notice too much difference in the way they perform. The other one, the SFH484, may require more care in pointing it. This one less care, but that one has a little greater intensity. This is a little less intensity over a given angular measure. Look at this chart. I didn't mention anything about this before on the other page, but there's really two representations here. One's polar, and the other's rectangular. And they're saying the same thing, and they do it this way because everything that happens on the left happens on the right. So we have the polar coordinate expression here on the left, and that kind of gives you a feel for the pattern, the nature of the radiation pattern. But the information is the same that's on the right here, where that's plotted out in rectangular coordinates. So you can see that we're usually interested in the angle at the 50% point. That's what the radiation measurement is, and you can see kind of here about what they're talking about. So the radiation angle is determined by the half radiation intensity, and so that's how you look at these charts. So that's the two SFH 484 and 485 devices. So here's the TSAL 6100. Notice that this is a 940 nanometer device, where the others I've just talked about were 880 nanometer. Both the previous one and this one have plenty of bandwidth, so you shouldn't worry about pushing that limit at all. If you look at this device, it has a half radiation intensity of 10 degrees. So that falls somewhere between the SFH 484, which was 8 degrees, and the 485, which was 20 degrees. So it's kind of a good compromise there. A lot more power, than than either of the other two. Let's see, I think we had 50 milliwatts for the 484 and 25 for the 485, and this one has 80. There's another interesting diagram shown here, and that is the radiant power versus wavelength, which I think probably is maybe not the most useful of all things that you need to know to use this device, because all it's really saying is this is an LED and it's not a laser diode. If it was a laser diode, then we would have something something like that, where basically all the light is very chromatic and focused at one very small frequency region. This is an LED, and the process of creating this light at the sort of the subatomic level kind of makes it contain all different components of light, and that's what's shown in this diagram here. Of no real significance, because go down to the 0.5 regions and look what we have. Let's go like that, and you're still pretty close to 940. You're certainly still in the 900 nanometers at the lower end, and so it's interesting, but it's not that significant to in making your choice for using this one or not. So replacing those QED devices on the old version of this this handout here is the IR333A. It's a pretty flexible radiator, and it has a lot of information here on this page concerning using it in the application that we have. So, for example, if you look at the page up here, the blocks up here, the radiant intensity is important to you. Notice that it's dependent upon the current, and if you want to see exactly how that plays out, take a look at that chart right there, and you can get differing radiant intensities depending upon the current that you use to drive this device. There's some things that are probably less important to you. Spectral bandwidth, don't really care about that too much. Here is another plot of that. Basically, it indicates that this is a 940 nanometer device. That's important, of course. The peak, so that's shown there. There's the operating ranges that you want to use it in, forward voltage and reverse current, and that's always important, of course. And then there's the viewing angle. The viewing angle is 20 degrees, and that's also in this chart over here. In fact, if you look at this chart off to the left, it says that it has a viewing angle, typical angle of 20 degrees. That's going to span between plus and minus 10 degrees like that. And so if you look at these radial lines that go out like that, these are the numbers here that pertain to that. And then if you look at these intensity lines that go around this way in the circular fashion, that's the radiant intensity. So the first one's like 0.9, 0.8, 0.7, 0.6, 0.5. So there is the measurement as indicated right there at half the peak intensity. So you can see that the intersection's kind of right there, if I've done that right, and of course that's 20 degrees. So the IR333 is another device that you might want to consider using. Okay, now let's look at the receiver. At the receiver, we can use a silicon PIN photodiode. PIN meaning, of course, positive intrinsic and negative substrates that are used to construct the device itself. Has a very fast reaction, and in fact, as you can see, this first device listed here, the VP104, operates at 5 megahertz. That's the maximum subcarrier bandwidth, that is. And so it's that pin structure construction gives it that speed. We have 2 pin photodiodes. I've also indicated here that a phototransistor could be used as well, but let's keep it straightforward and not be experimenting with phototransistors, so we'll use the pin diode, this one and the one on the next page. Okay, so first of all, there's the BP104, and as I said, it has a maximum bandwidth of 5 megahertz, which is well above anything that you'd be expected to use in here. And here's the characteristics of this. The characteristics that are shown below, that is being the sort of the viewing angle and the response frequency range. You can see that first of all, this device is fairly broad in spectral sensitivity. It will work really well on the 940 nanometer type of device, but it also work well for the 880. Of course, the 880 nanometer would probably be down in there somewhere, and around the 940 be closer to the maximum peak right there. But nevertheless usable for either one of those types of radiators. The other chart to the left here indicates another important characteristic of receiver devices, optical receiver devices, and that it has a very broad viewing angle. In fact, we'll go through the logic that I used before, looking at the 50% angle. Go from there to there. Well, okay, so if you extend this out on both sides right here, you have about 30 something odd degrees, somewhere between 30 and 40 on either side, so the total viewing angle then is about 65 degrees. And actually this says plus or minus 65. I'm not really sure that that's probably down a little bit further. Maybe I should change that. It should just be 65 degrees. And so anyway, it's a broad viewing angle. That's the important thing, because the broad viewing angle makes the pointing from the transmitter easier. So it's always more desirable to point the radiator, because that's the thing you're using that radiates energy. You want to keep that as useful as possible, so keep it narrow, keep the beam width narrow. And the receiver then would be better if it had a wider beam width, that is a wider angle of sensitivity. So that's the BP104, and so that one is available for you to use. The next device that we have is the SFH206K. It has a maximum subcarrier bandwidth of 25 megahertz, which is of course even higher than the previous one. This device sort of complements the other device in its range of spectral sensitivity. So I have the question mark here. What's the range of spectral sensitivity of this device? Well, if you look here, if we use the 50% mark as the standard, which we're going to determine that sort of thing. Here it looks like it goes to like 550 nanometers all the way up to over 1,000 nanometers. So it's a fairly wide frequency range device. But the interesting thing here is this one sort of peaks up at 880 nanometers, and you can also use it for 940 nanometers without much loss at all. So it'd be kind of like maybe right in there, so still up above the 90% sensitivity range. So the other device, the BP104, was this curve was kind of skewed to the left a little bit, and kind of peaked out on the 900 and 940 nanometer device. This one peaks out on the 880 nanometer device. And then if we come over here and look at this half angle sensitivity, doing the same kind of analysis that we had before, going to 0.5. Okay, so that comes around to there and there, and if we'll be reading the same thing on either side. Go down, and that's 60 degrees there. That intersects at 60 degrees there, so I would say the angle of half sensitivity is like 120 degrees. Yeah. And so that's a pretty wide range, wide viewing angle device as well. So both of these are usable devices that you can implement into your design for this project. Okay, so the final topic is the drive circuitry for the LED, and here is a typical schematic shown here on this page that will show you how that you might go about doing that. And we have this device. Well, actually, no, it's not this device. It's the ZTX602 we have, and we also have the 2N2222 switching transistors, and either one will work fine. Okay, the notice here is that there are two ways to increase the transmission distance in an LED communications link. First of all is to increase the power of the transmitted signal, and you've seen how you can do that. You know, and most of these devices increase their radiant energy or radiant power with an increase in current. And the other is to focus the signal more precisely on the receiver, and that's something that's typically done in RF, and it's also done in optics. And of course that would mean that we would have some sort of magnifying lens present to do that. So one of the things I had mentioned before is keep the number of LEDs down to no more than 4. This is not a project where we're trying to achieve maximum range. We just want to demonstrate free space transmission capability, and we're not looking for long range performance out of this. So an array of 4 LEDs should be enough to accomplish the minimum distance requirement for this project. So let's start with that in mind and see how we go in getting transmission or propagation distance with this project. And finally, here is several schematic diagrams of LED drivers. 2 of them at the top are PNPs, and at the bottom they're NPNs. So this gives you an idea how to drive these things. They're pretty straightforward. And so kind of look at this. This is taken from a reference that I think I put on the technical page. So there's a number of different ways, of course, that you can drive LEDs. They are, after all, simply LEDs, and when they're biased in the forward direction, they conduct current and they emit light. So it wouldn't be any different than biasing a Zener or something like that. So you got to have enough current to pass through them to light them, and you can adjust that current to get different intensities, but of course not so much so that it destroys the LEDs themselves. So there's some examples of how you might drive the LEDs at the transmitter.